Hi, welcome back to McClatchy Maths. My name is Natalie McClatchy and we are continuing our series today on arithmetic sequences and their applications by talking about depreciation. In this video, you'll find out what depreciation is, how to represent it in a recurrence relation or use a general rule to calculate depreciation. We'll also talk about depreciation in the context of usage, which will make more sense as we get into the video. And then finally, we'll quickly wrap up talking about what's coming up next. This particular video is aimed at our senior maths students in grade 11 and 12. However, if you're studying business or accounting, there are some different crossovers that may interest you there as well. So let's kick off firstly and talk about what depreciation is. Depreciation is a process that takes place upon an asset, in a business particularly, where it loses its value over time. Now, an asset is something that you own. So in a business context, that could be a company car, it could be a truck or a tractor, it could be factory assembly line equipment, it could be office furniture, it could be photocopiers, and the list goes on. So different kinds of businesses have different kinds of assets, and over time they lose their value on paper. Now, we've got to remember that when we're talking about depreciation, it's a theoretical process where we actually change the value of that asset on our accounting books over a period of time, because we recognize that the minute we drive, for example, a car out of the showroom doors, then that car has started to lose its value and we can't sell it and get the same amount that we paid for it. So that's why we have this process of depreciation in place. Now, businesses do calculate it once a year, typically at the end of the financial year, and they take each of their assets and they reduce them by a certain amount in their accounting documents. That's what you've heard me refer to them as the books. And this ensures that a business's reports that it communicates to its owners. Now, businesses are either owned by a mum and dad if it's a sole trader, or by partners, or even by shareholders if it's listed on the stock exchange or if it's a company. So they actually want to know the true value of all of the assets that are in the business. And that way, if the business had to be sold, or every asset in the business had to be sold suddenly overnight because the company's gone into liquidation due to financial difficulty, they want to know that the amount of value that that asset has on its balance sheet is actually equal to what they could get if they sold those assets. So if you simply left the value of, for example, $2 million worth of assets on your books at what you purchased them for, that no longer reflects what they are worth in reality. Now, there's different methods of depreciating assets, and we're focusing on straight line depreciation, which is what occurs in arithmetic sequences. When we come to our geometric sequences videos, we'll be looking at different depreciation methods, but here we're focused on what's called straight line depreciation. Now, you can imagine if we were to graph it, because it's an arithmetic sequence, it depreciates in a straight line. And we talked about that in our introduction to arithmetic sequences videos, because arithmetic sequences always are graphed and they show a straight line growth or decline. Now, in the case of depreciation, it's always going to be decline because the asset's losing its value. That's what depreciation means. Okay, now eventually, every asset in a business, if we're taking its amount down every year by the same amount, it's going to get to the point where it's worth nothing in the books. It's got a value of 0. And at this point, we say the asset has reached its scrap value. Now, there's some different terms that you'll see in different exercises, exams, where they refer to scrap value using different names. Sometimes it's called the residual value, sometimes it's called the salvage value. You just need to be aware that it can be called different things. They all mean the same thing. It's basically reached the point where the business is either going to scrap it literally by chucking it out, or where they take it to the dump, or they recycle it, or they just sell it on to whoever will give them the best price. So typically in the books, that's when it's reached a certain number. It may not always be 0. Sometimes a company might decide that when all their company cars reach the value of 10,000 in the books, they'll sell them. That's their scrap value in that particular context. But if you're not told what that scrap value is, it's assumed to be 0. So we can write this as a recurrence relation. This is not on your formula sheet. And in this particular case, our value, so you'll remember from our simple interest, that looks a little bit like this. Our value at time 0, which is when we actually purchase the asset, it's going to be equal to A, which is the purchase price. And then the second half of our recurrence relation, remember, is a formula. Vn plus 1 equals Vn minus D. And D is the actual common difference But it's also the depreciation. It's kind of handy that it both starts with the same letter. It's the depreciation that's taken away every year. So here's some of our variables, and n once again is the number of years, whatever year we're up to. Okay, so we take that common difference away every year because we're losing value. If you had an actual asset that was appreciating in value, and sometimes you might see that perhaps on a complex, unfamiliar question, where the asset actually grows in value every year, then you're going to be adding that common difference instead of taking it away. Let's look at our first worked example. We've got a few in our video today. Hopefully these will be helpful to you. So we've got an Uber driver who buys a new car for $30,000 and it's depreciated by $5,000 every year. And all we have to do is write it as a recurrence relation. So easy peasy, we just simply write out our basic form. That's why it's good to know that form off by heart. And then we're going to substitute the two values that we have in. So firstly, we know our starting value is V0, it's 30,000, and our common difference, or the amount of depreciation every year, is going to be 5,000. Let's put that into our equation, substitute it in, and we've got our recurrence relation. Very easy. That was worked example 1A. Let's look at 1B. Now we've got to calculate, using our recurrence relation, the first 3 years of depreciation. And we've been asked to put this information into a table. It's always a good idea to present this kind of information in a table. It certainly communicates your information a lot more simply. So we've got on the side N0, 1, 2. Now they've asked for the first 3 years. You might be thinking, well, hang on, that only takes me to the end of the second year. But we've actually got N equals 0, our first value, which is the amount at the start of the first year. So that's why we only need to do 2 rows, years 1 and 2 basically. So our value for T is going to be the same every year. It's always depreciating by 5,000. So our first row, we take 5,000 off 30,000 and we get our value for the year, end of the first year. It's going to be 25,000. That will come into our second row and move down. Take 5,000 off again, we get 20,000. And the value at the end of the row starts our third row, which is year 2. And we've got 3 years of depreciation, takes us to $15,000 at the end of the second year. We can also write a rule for depreciation, and this makes it a lot easier to work with. Rather than having to work out every single year, we can actually just substitute it into a simple rule. It looks a bit like our arithmetic sequence rule, but you'll notice in this case, instead of term 1, from our formula sheet, we've got value at times 0. And instead of doing n minus 1 in brackets and multiplying that by d, we just multiply n by d. Now it's very important that you don't use the rule from your formula sheet for depreciation. It's a little bit different. We're using 1 less here because we're starting at time 0 and at the end of the first year, which becomes the beginning of the first year for the next row, like we did on our previous example. So we don't need the n minus 1 in this case. So let's look at an example and apply the rule. We've got a motorcycle purchased for $22,000, depreciating by $3,000 every year. We need to calculate its book value after 7 years. Now, the reason why it's called a book value is because that's its value on paper. You might actually be able to sell it for more if you're lucky. You might have to sell it for less. You never know. Okay, so we're going to use our general rule, and n is going to be equal to 7. So we simply substitute it into the equation. The value at the end of the 7th year is 22,000 minus 21,000. It's valued at $1,000. Hopefully you could get more for your motorbike than that if you've paid $22,000 for it. So we also need to write a statement at the end. And the reason for that is the question doesn't have the variables V7 in it. So we need to actually write V7 equals 1,000 and then create a statement. The book value is $1,000. We're going to apply the rule again in a different scenario. A tablet is purchased for $2,000 and depreciates at $350 per year. Calculate the number of years for the tablet to reach its scrap value. Now we're going to use our rule again in this case and substitute the information that we know from the question. So we know that V0 is 2,000. We know that our value for D is going to be 350, but this time we don't know the number of years, so N will remain a variable. We do, however, know the value of Vn, and we're putting that in as 0 because we haven't been told what the scrap value is, so we can assume that its value in the books is going to be 0. So now we're going to manipulate and transpose our algebra with both sides. We'll take 2,000 away. And then we're left with negative 2,000 equals negative 350n. Divide both sides by negative 350, and if you pop that into your calculator, you're going to get the answer of 5.7. Now, typically depreciation doesn't happen in the middle of the year. It happens at the end of the year. So at the beginning of that 5th year, there is still some value. The tablet hasn't reached its scrap value yet. So it's going to reach its scrap value when it gets written off at the end of the 6th year. So we need to round that one up. Let's talk a little bit now about depreciation involving usage. In all of the examples before, we saw a fixed amount being taken off the value of the asset at the end of every year. But some companies decide not to go by years, but rather by usage. So instead of it being a fixed amount per year, it'll be, for example, on the number of kilometers a car may have been driven. Or another example might be on a photocopier. We might go with number of copies that it does, and then we take some value off each year depending on how much it has been used. So our usage of our car will also be decreased by its usage, but also by its age. So I'll give you an example of this, and we call this unit cost depreciation, where we're affecting it by the usage. It's another form of straight line depreciation. So we're going to use our rule again to calculate depreciation using this kind of usage. But instead of D being a fixed amount every single year of depreciation, it'll actually be the amount of depreciation per output or usage. So that output might be the number of kilometers driven or the number of photocopiers taken. So D could be 30 cents per kilometre for a car, or 5 cents per copy for a copier, or even $1.50 per product produced in a factory that makes products. So let's have a look at how that looks in an example. Worked example 4. A semi-trailer truck was purchased for $175,000 and depreciated using the unit cost method, 50 cents per kilometre. Complete the depreciation table below. So in each case, we know how many kilometres were driven, so the amount of depreciation that comes off it each year is going to be different. So our starting value is $175,000. To work out the depreciation, I take the 32,000 kilometres and I'm going to multiply that by 50 cents per kilometre. So it's important to put that from cents into dollars. And then I'm going to work out that the depreciation is $16,000 and put that into the table. So my future value now is going to be the $175,000, take away the $16,000. That'll give me a future value of $159,000. Oopsie, too many zeros in that one there. Did you notice? Okay, now that future value comes down as the starting value for the year 2016. And once again, we're going to multiply that 45,000, which is the kilometres for this year, by 0.5. And we've got a different depreciation amount because more kilometres were driven that year. And so our future value, we're going to take that off, and our future value is going to become $136,500. That becomes our starting value again. And we follow that process all the way through to the end. So the more kilometres that you drive, the more depreciation in a particular year. And that makes sense. If you spend a lot more time using your actual asset, it's going to wear out a lot faster than if it's not used very much at all. Let's look at another worked example. A company car is purchased for $58,000 and depreciated at a rate of 25 cents per kilometre. The car is going to be scrapped at $20,000. So how many kilometres will we have to drive before we scrap it? So in this case, our scrap value is not zero. So when we use our general rule, VN will actually equal 20,000, which is the scrap value. It's going to then be equal to the starting value, V0, of 58,000, take away N times 0.025. We've got to find N, that's the number of kilometres, and 0.25 is the depreciation rate, D, the common difference. Okay, so let's simplify both sides a little bit more, and then we divide both sides by negative 0.25 to get N all by itself, and we're going to find N is equal to 152,000. So we need to write that as a statement because we didn't get asked to find N in the question. Our statement is the car will reach its scrap value after driving 152,000 kilometres. Let's look at another worked example. A photocopier is purchased for $9,200 and it's depreciated by a percentage of the purchase value, and it will be fully scrapped in 5 years. What is the annual depreciation amount and what percentage is this of the purchase value? Now, when you get onto geometric sequences, you're going to find that when they use depreciation, they use percentage reduction. Now, you might be confused when you come across a question like this and automatically think when you see the word percentage that it's going to be a geometric sequence, but it's not. It's simply a percentage of the first year only of the purchase value, and it's going to be depreciated by that amount every single year. So we use our general rule for depreciation again. Our starting value is 9,200. Now we're saying fully scrapped, so that means VN is going to be 0 minus 5D, and we've got to find out what that depreciation value is. So if we simply rearrange our formula again, we've got D is equal to 1,840. So what that's telling us is that it's being depreciated annually by $1,840. Now we said it was a percentage of the purchase value. What percentage is that of 9,200? So that we're going to simply substitute that in and turn it into a percentage. It's 20% of the purchase value. This question could have been reworded differently. They might have said a photocopier is purchased for $9,200 and is annually depreciated by 20% of the initial purchase price. So then you would have to work backwards, calculate 20% of 9,200. You'd find that was $1,840, and that's the amount you depreciate by every year, not 20% of the previous value, but 20% of the purchase value. I'm going to do some questions like this when we get to complex later on so that you can retest these skills with that one. But let's just quickly talk about what is coming up. Our next video is on population growth. I don't see a lot of this actually run through in examples in textbooks, but they do ask questions about it all the time in exams. So we're going to cover some population growth and some complex questions. We'll move on to some math methods work, looking at some of arithmetic sequences and a whole little mini series on geometric sequences. Welcome again to all of our new subscribers. Thank you so much for joining us at the channel, and why not follow us on McClutchy Maths for more McClutchy Maths in your day. Thank you again, everybody, for joining us. You can email me at mcclutchymaths@yahoo.com, and I hope that this has been a helpful video to you. Have a lovely day.